two lectures in this week's is kind of revision and just some language. We're going to start the material proper now. So last semester, you learned how to find the slopes of tangents to curves that are graphs of functions. So there's something, we'll kind of explain this in a second. So if I draw the graph of a function, I'm going to be starting over on the left and ending up on the right, or basically moving left to right or right to left, and I can't go back on myself. So let me explain this. So say something, well, we usually draw this cubic kind of a thing. So I'll draw a curve now that isn't the graph of a function. So something like that. So the red thing is definitely the graph of a function. So let's see, this will be y is equal to f of x. But the blue curve, is not of that form, because if you consider this input, let's call it x0, there's two y coordinates. So I say x0, y1, x0, y2. But a function, you put an input, there's only one output. So, and the graph is all the points of the form input, output. So this kind of says x0 has two outputs. But that's not a function. Not a function. So there's something called the vertical line test. And if you look at the red curve, if you draw any vertical line, it hits it only once. But if you draw that one, or in particular that one, on the blue curve, it hits it twice. So it's not the graph of a function. Now, the normal differentiation you learned about last semester was for the red curve, but we're going to look at kind of things more like the blue curve. So we're going to learn how to find the slopes of two more types of curves. So the first one is what's called a parametric curve. Now, what you probably want to think about this is it's something moving in two dimensions, perhaps as a function of time. So we'll start here and we'll say this is time equals 0. So it'll be at this point. And just imagine it moving around, and it can do lots of, it can intersect itself, it can kind of come over. It may close in on itself, or maybe not, or it can go off to infinity or something like that. So that was t equals 0. So at all these different times you're getting, so maybe this is t equal to 1, this is t equal to 2, maybe this is t equal to 3, and like maybe this is t equal to half, etc. And so you just imagine it going around, and you can also have a negative time. That's not actually a problem. So this portion of the curve is negative time. Okay, now the way we write this down is we have that's kind of the way I want you to think about a parametric curve. But what you're going to have is that at every point, or there's going to be, so the x coordinate is a function of time, and the y coordinate is a function of time. So, for example, if you go to t equal to 4 here, there's going to be some function for x, which you input in the time equal to 4, and you'll get the x coordinate there. There'll be some function of y, you put in t equal to 4, and you'll get the y coordinate there. So what really a parametric curve is, there's kind of three variables, x, y, and t, and what you're plotting is the x and the y as the t changes. This is kind of the idea here. So hopefully over the course of these examples, if that doesn't make sense yet, it will make a bit more sense in time. So if we've got x of t, y of t are functions of t, so we get the set of coordinates. So we do the set of coordinates x of t, y of t, as t runs over some set of possible inputs. So that's just a collection of points. X and y are functions of t. Put in different inputs to x and y, you get different points. These are what are called parametric curves, and you can come back on yourself. That's no problem. Okay, so suppose you want to find the slope of the curve at a point, Well, how does this work? So we'll write down some parametric curve. Suppose it does something like that and it goes off. Suppose it starts here. Suppose it's negative time, it goes off here that way. Okay. So what you do is we're going to look at a point t0. And let's just say it's this point here. So this is x of t0, y of t0. Now the idea is that if you zoom in close enough, you have the graph of a function. So I don't think I actually can zoom in close enough. So what you have to do is you want to zoom in and just avoid vertical bits. Now I'm just going to put big black squares where all the vertical points of the graph are. Just about avoids going perpendicular there. Yeah. Okay, so actually what this is you've got a number of components here. So it's a number of functions glued together. So if I go from this point to this point, this is like y is f1 of x. Because if you look, so let me say, let's call this the point P1 to, let's call this P2. So from if you look at the curve from point 1 to point 2, it passes the vertical line test. So you've got this big theorem that says if you've got a curve which never goes vertical and it satisfies the vertical line test, then it is the graph of a function. Okay. Similarly, you can go from P1 to P3, and that's the graph of another function we could call f2. From P3 to P4, you have another function which we could call f3. Then you've got a big function going from P4 to P5, and that's the one we're going to call, I think we're actually going to call it y. Yeah, we're going to call it y or f. And then you have another one, P5 to say P6. That could be another function, we call it f4. So basically what you have is you've got loads of parts of graphs of functions glued together. So we're just going to focus, we're interested in the point t0. So we're actually just going to look at between P5 and P4. Now the important point is, as long as the slope is not vertical at t0, you can kind of take a portion of the curve. So see this green bit? That is the part of the graph of a function. It's like the red thing here. So in this region, we're going to say, in fact, y is equal to y is a function of x. And in turn, we have that x is a function of t. So we're saying locally means near the point, the part of the parametric curve near a point like this one forms the part of the curve of the graph of a function. Okay. Now what we want to do is we want to find the slope. The slope of the tangent. Now the tangent to the red curve is the same as the tangent to the green curve. That's drawn really badly. Yeah, it's better, yeah. So I'm trying to say that the slope of the purple line is the same as the slope of the tangent to the green line. So what I can just do is I can differentiate the green line. So I think what I have to do here is I need to end up differentiating this green thing with respect to t. Now I might say, what? Well, let's do it. So let's differentiate the green curve, which is y of x of t, with respect to t. Now you've got an outside y and inside function x, so you're going to use the chain rule. So the chain rule says differentiate the outside function, that's y dashed. The chain rule says evaluate at the inside, and that's x of t, or I could just write x, times the derivative of what's inside, but with respect to t, so that's dx dt. Now, what we have now is that this is the derivative of y essentially with respect to x. So this bit here is in fact equal to dy dx of the green curve And the dy dx of the green curve is exactly the slope of that purple line, which is what we're interested in. So what we actually have here is, if we write this again, now what we have to kind of take is that if you're differentiating y of x, well, y of x is y of t is y basically. So the thing on the left hand side is dy dt equal to dy dx times dx dt, and if you divide both sides by dx dt, you get, and this is the important thing, dy dx is equal to dy dt divided by dx dt. Now sometimes differentiation with respect to t is done with a dot. So like a dash would be differentiation with respect to x. A dot would be differentiation with respect to t. So you could write y dot over x dot. Now I won't actually be using that, but it is something you could do. Now this is what you need. Now you might notice that if the derivative of x with respect to t is 0, if you analyze what that means a vertical tangent, and if the x dt is 0, this thing in the purple box is not defined, and a vertical slope is not defined because it's like division by 0. You can also find the second derivative. Now it's a little bit messy, but we'll see how it goes. I think I'm not going to ask you to calculate a second derivative, but I need you to know what we looked at 2 lectures ago about. So the thing about the second derivative being positive is a U-shaped second derivative, and a negative shape is an N-shape. I will be interested in that, and I think we'll see it again here. So, but anyway, the differentiate with respect to x operator goes like this, and if we use that, we see that, so we're going to use that on dy dx. So in other words, put in for this black dot dy dx. So you differentiate with respect to t, and you divide by dx dt. And the thing on the left is differentiate with y with respect to x twice. So we've shown that the second derivative for a parametric curve is the derivative with respect. Now this is why you can't just say differentiate, because on the top you've got, oh, you differentiate twice, but with respect to what? First x and then t. And I suppose the important thing to note is that this is not equal to, say, the second derivative above and below. It's just not that simple. And the second derivative above and below could be written as y dot dot over x dot dot. Okay. So if I am going to ask you to do this, I'll give you the formula. Well, I suppose you have the formula anyway. Okay. So let's start doing some examples. Okay. So a curve is described parametrically by these equations. So this is the x coordinate in terms of t and the y coordinate in terms of t. Find the slope of the tangent line to the curve at this point. Now it's going on about this y minus y1, but I don't think you actually need that because it's just looking for the slope. So the slope of the tangent line is just the m, and the m is dy dx. So we got m is equal to dy dx. And we've just shown on the previous page for parametric equations, dy dx is dy dt divided by dx dt. So what's the derivative of 3t? Now you might say, oh, say 3. For later on, I'm going to get into this big thing about constants and term by term. So if it's a constant times a function, the scalar rule says fix the constant, fix the 3, and then differentiate the t. And the derivative of t with respect to t is 1. That's 3 by 1. And then dx dt, fix the 3. And what's the derivative of t squared with respect to t? 2t. So we're getting 3 over 6t. And we can leave that like that. Okay. So now the question becomes, you have the slope in terms of t, and the question is, for what value t do we reach the point 12,6? So like if you plot this thing, now I actually probably could plot this properly, but I'm just going to plot it in a stupid way. So at t equal to 0, the x and y coordinates are equal to 0. So now it doesn't do this, but say it goes off and does this thing. And the question is, at what point, after what amount of time, am I at the coordinate 12, 6? So t equal to what at 12, 6? Because you have the slope in terms of t, it's 3 over 6t. But the question is, yeah, what's the t value? So how you do this is you say, okay, so the x is in fact equal to 3t squared. So you want that to equal 12, and you want y, which is equal to 3t, to equal 6. So you want to find a time that the x coordinate is 12 and the y coordinate is 6, but we have the x and the y coordinate in terms of time, or t. So we want 3t squared equal to 12 and y and 3t equal to 6. Okay, now what you should do here really is solve one of them, which is the easy one, and check the solutions in the other one. So the easy one is on the right hand side. So if I just have t multiplied by 3, so if I divide both sides by 3, I get t is equal to 6 divided by 3, which is 2. And all I have to do is just check this. Does that work? Because it could actually happen, like, say for example, it's 12, 3, and I don't think that point isn't actually on the curve. So it doesn't make, you're not guaranteed that a point is on the curve. You're not guaranteed that there's a time it hits there, in which case the question doesn't make sense. And anyway, let's check it. 3 times 2 squared is equal to 3 times 4, which is equal to 12, correct. So at t equal to 2, you are indeed at the point 12, 6. Just for argument's sake, so also, suppose you didn't recognize that the y equation was easier to solve and you solved the other one. There's just something to look at here. So 3t squared is equal to 12. Divide both sides by 3, so you get t squared is equal to 4. Now it's very important when you're solving an equation with a square that there's actually two solutions. So you can say, oh, I'll do the square root of both sides, but you have to remember there are two solutions, plus or minus. So plus or minus 2. And then when you look at the y, plus 2 works, but minus 2 does not. But if it was 3t equal to minus 6, you would have needed the minus 2, but it's not. So it doesn't really matter. Okay, so I'll just write y is positive, so t has to be positive as well. Well, that's, yeah, the y value is, well, let me see. Well, 3 times minus 2 is equal to minus 6 is not equal to 6, but the other one does work. Okay, because actually it is possible that there's 2 times. You could actually go back on yourself. So in terms of our picture here, this won't happen in your examples, there'll only be 1 time, but it could actually happen that there's 2 times. So you could have some negative time. And of course, at that negative time, minus 2, the slope is very different. Yeah. So anyway, we found that the time that it reached this point is 2. So all we have to do is put t equal to 2 into the slope. So it's 3 over 6 times 2, which is 3 over 12, which is equal to 1/4. Done. Okay. So that's one example done. Let's do another example. So what have we got here? Bezier curve. It's a parametric curve popularized by a Renault engineer who used them for designing curves for automobile bodywork. Just to kind of explain what they're doing. So you pick 4 points. You go through 2 of the points, as you can see, but the bit that's missing is that the slope at, say this is, I think t equal to 0. I think the other one I think is t equal to 1. Be careful here. Yeah. But the slope at t equal to 1 is precisely the slope of the line from there to there. So what it's doing is you're specifying the 2 points on the curve and the slopes at those 2 points. So what I'm saying is that those 2 green lines are tangents, and this question is about showing that. So this particular curve is given with these equations. I might have to write them down for myself for the next page. Okay, let's see what the questions are about. So the 4 points are given here. P1, P2, P3, P4. The parameter t runs between 0 and 1, such that, yeah, you're at P1. Maybe we'll just do, we'll label P1 and P4 anyway. So this is P1 and this is P4. We might come back to the other points later, which we'll do now. So P2 is 1, 3. This is P2 and necessarily this is P3. Okay, the parameter t. Okay, so at t equals 0, it's at P1, we've seen that, and at t equals 1, it's at the other point. Find dy dx. So that's the first thing. So that's just going to be dy dt divided by dx dt. So dy dt, excuse me, dy dx is dy dt divided by dx dt. Now I've just written down for myself these formulas, but I'm just doing the derivative of y with respect to t divided by the derivative of x with respect to t. And I'm going to fix my constants and stuff. Now, because they're sums, they're very easy. You can differentiate term by term, fixing constants. So the first, you got 9t. So I'm going to fix the 9, and the derivative of t with respect to t is 1. Fix the minus 6, and the derivative of t squared with respect to t is 2t. And fix the minus 2, and the derivative of t cubed is 3t squared. And now do the same for dx dt. Fix the 3, the derivative of t is 1. Fix the 6, the derivative of t squared is 2t. Fix the minus 3, and the derivative of t cubed is 3t squared. Now we will simplify this. We could probably divide above and below by 3, but we won't bother with that. We get 9 minus 12t minus 6t squared, and 3 plus 12t minus 9t squared. Now, so we could divide above and below by 3, but we won't bother. That's dy dx. Hence, find the slope of the tangent to the curve at P1 at t equals 0 and t equals 1. So all we have to do is just substitute t equals 0 into that. So at P1, all I have to do is substitute t equals 0 into that. Now, what is clearly going to happen is all the t's are going to be 0. So you're just going to end up with 9 over 3 is equal to 3. Okay, and at the other point, which is P4, is that what it says? At P4, yeah. So this is t equal to 1. So just substitute t equal to 1 into this. So you're going to end up with 9 minus 12 times 1 is 12, minus 6 times 1 squared is minus 6, over 3 plus 12 times 1 is 12, minus 9 times 1 squared is minus 9. And what are we talking here? Looks like 9 minus 18 over 15 minus 9. That's minus 9 over 6, which we can leave, but it's also minus 3 over 2. Okay, if I haven't made some stupid mistake. And probably a good thing to note, so if we look at them, note one is positive, one is negative. And as you can see there, so the first tangent here is positive, the second one is negative. And although it doesn't look like it, the first one is steeper because it's 3 versus 3 over 2. So what's question C? Show that the slope P1, P2 is equal to the slope of the tangent. So the slope of the line segment P1 to P2. So that's this one. So this is P1, P2. And just show that the slope of that is the same as the slope of the tangent, which we just calculated to be 3. Now you can use a slope formula, but rise over run is better. So just looking at P1, P2, so right, the slope of P1, P2 should be the rise over the run. So it goes from, in terms of y's, from 0 to 3, which is 3. And in terms of x's, it goes from 0 to 1, which is 1. So if you just make a little triangle here, right angle triangle, and do slope as rise over run, this is 3, this is 1, so you get the slope is 3 over 1. Or you can use the slope formula. I like rise over run, we'll write it here. So the slope of P1, P2 is rise over run. The rise was 3, the run was 1, and that's equal to 3. And what does the question show? The curve is equal to the slope of the tangent as calculated. So that's the same as dy dx at t equals 0, as expected. Okay. And then, is the second derivative positive or negative? Explain your answer by appealing to the graph. So look at it. There's even a hint here. Look, sad face. It's an N shape, negative second derivative. So all you have to write here is the second derivative positive or negative. Second derivative is negative as it has this shape. Done. Another example done. Don't think we'll go on to, yeah, we'll keep going, I think. Okay. Yeah, it'll make this one a bit long, but how bad? Okay, so an asteroid, that's this shape here, is defined parametrically by these. Now, don't be afraid by the theta. Here we just have theta instead of t. It's basically the same thing otherwise. An asteroid is the curve traced by a point on the rim of, yeah, you can imagine about what that is. So I think you have, we could draw this, but I'll maybe try and draw a little bit of it. I could make a fool of myself though as well. This is supposed to be a circle. And so what you have is a ball rolling. Now the ball has radius 1. So you have a ball rolling inside another ball. So look at this point. As that rolls, this point here traces out that shape, is the idea. So it's the curve traced by a point on the rim of a radius 1 circle as it travels around the inside of the circle of radius 4. Parameter theta is given by the angle POX. So in terms of the angle, so for example, if I talk about this point here, what's the value of the parameter? Is that angle there, like that. And so you have, it's just, so what that actually means is the theta goes from 0 to 2 pi. Now we have to be in radians because we've got differentiation. Have to. Okay, so what are our questions here? Find dy dx, that's no problem, dy dt over dx dt. Hence find the slope of the tangent line to the curve at theta. So we're just going to plug in theta equal to pi over 4. And then we're going to talk about N shape, U shape. So not too bad. Okay, so we need to differentiate these things up the top. So I think I'm just going to write them down for myself. So I'm just going to write down those things up the top on a separate piece of paper. Okay, so I'm going to do here dy dx is equal to dy dt divided by dx dt. So y and x are above. So I'm going to differentiate y first, term by term, fixing constants. So fix the 3, and I've got sine of theta. What's the derivative of sine of theta? Cos of theta. Minus, now I have to differentiate sine of 3 theta. Now sine of 3 theta, you've got an outside function sine of x and an inside function 3 theta. So you have to use the chain rule. So the outside function is sine of x. The chain rule says differentiate the outside function. The derivative of sine of x is cos of x. The chain rule says evaluate at the inside. The inside function here is 3 theta. And then the chain rule says multiply by the derivative of what's inside. So I need to differentiate 3 theta with respect to theta. I'm going to fix the 3, and the derivative of theta with respect to theta is 1. Okay, now differentiate x with respect to t. So I've got 3 cos theta. I'm going to fix the 3, and the derivative of cos theta is minus sine of theta. Now that, as written, is wrong. I add that bracket to make it correct. Plus, now I've got cos of 3 theta to differentiate. That needs the chain rule. So the outside function is cos of x. The derivative of cos of x is minus sine of x. So that's the first part of the chain rule, differentiate the outside. Then the chain rule says evaluate at the inside. The inside is 3 theta. But then you must multiply by the derivative of what's inside. and the derivative of 3 theta with respect to theta, fix the 3, and the derivative of theta with respect to theta is 1. And now we're just going to tidy this up. Now we could simplify it by dividing above and below by 3, but I'm not too worried about that, to be honest with you. So I have 3 cos theta minus, so I got cos 3 theta by 3. Now that 3 theta is not multiplying. So if I just, this is a single number. You can't just multiply in the 3, that doesn't make any sense. So what I'm saying here is I've got cos theta by 3. Even if I write cos theta by 3, does that mean cos of 3 theta by 3? So to get over that ambiguity, I write it the other way around as 3 by cos 3 theta. And on the bottom, now 3 by minus sine is plus by minus is minus. 3 by sine theta. And then we have plus minus, which is minus. And for similar reasons as above, we write the next thing as 3 sine 3 theta. I said you could simplify it by dividing above and below by 3, but we won't bother. So that's dy dx done. Hence find the slope of the tangent to the curve at pi over 4. Now one thing we might just notice, look at the tangent at pi over 4. It's negative, it's going down. So we should at least expect to get a negative angle. So excuse me, negative slope. So we're going to do dy dx evaluated at theta is equal to pi over 4. So I get 3 cos pi over 4 minus 3 cos 3 by pi over 4, in other words 3 pi over 4, divided by minus 3 sine pi over 4 minus 3 sine 3 pi over 4. Now, if you're in radians, you can, of course, just bang that into the calculator, and that's perfectly okay. I'll try and do a little bit better here. So pi over 4 is 45 degrees, and the sine and cos of 45 degrees is 1 over root 2. So I have 3 over root, I might have to go into the calculator at the end anyway, minus 3. Now 3 pi over 4 is like 135 degrees, so you're over in the second quadrant, and the cos is the x coordinate, so it's going to be minus cos of 45 degrees. Similar story, we get minus 3 over root 2. Like this can be done on the calculator anyway, if you don't like this. And then if we look at it, you can multiply above and below by root 2, and you'll get 3 plus 3 over minus 3 minus 3, 6 over minus 6, which is equal to minus 1. You could have gone to the calculator much earlier with that. What's good? It's negative, as the picture suggests. Okay. Last question, is the second derivative positive or negative at that point? Explain your answer either by appealing to the graph or calculating. Now, I don't recommend that you calculate. All you have to see is that at that point, it's part of a U-shape. Now, you might say it's not U-shaped. Well, look what's happening with the slope. Here, it's kind of big and negative. And here it's kind of going towards 0. So that means that the slope is increasing. And that means that the first derivative is increasing. That means that the derivative of the derivative is positive. The second derivative is positive. But I think it's just easier for us to say in this region, if you keep going, you'll get a U-shape. So we're just going to say that the second derivative is positive because it's a U-shape. Well, the second derivative is positive as it has a U-shape. Done. Okay, we'll pause. Actually, what we're going to do, yeah, we'll pause.